All right, so we were talking about energy methods, right? We spent quite some time on energy methods, so hopefully that helps us to be comfortable with that topic at this point. Now, what I want to talk about for next, I think this week and next 2 weeks in terms of number of lectures, maybe next 4 lectures, including this one, is principle of impulse and momentum, and then impact. Now, what is basically in general momentum method? What are momentum methods? Now, when we were looking at energy methods, right, we were looking at the relationship between force and displacement, right? Or remember, we were integrating, we basically integrated Newton's second law with respect to position, and we said the integral from position 1 to position 2 force dot product dr is equal to change in kinetic energy. Now, what we want to do in momentum methods is that we are integrating Newton's second law with respect to time. So what happens is that now what we care about is the relationship between force and time. So that's the big change that we have going from energy method to momentum methods. All right. So let me write it here. Momentum maybe I can do a little better methods. You can write we look into the relationship between, well, let me write it. The relationship, we look into, it's supposed to be I, into the relationship between the time integral of forces and change in the object's velocity, in the linear momentum, in the object's, I'll tell you what linear momentum is, in the object's momentum. That could be linear or angular. So we determine, using these methods, we determine the change in object's velocity when there is some external force, some unknown, some known force is applied to a system, and we know that force as a function of time. Right? So we can use that to, again, study the object's velocity, looking to analyze the impact between objects. That's what we're going to talk about later on. And also we can evaluate forces exerted by continuous flows of mass, but that's not what we do, at least within the scope of this course. But that also fits into this category when you look at momentum methods. So we start with principle of linear impulse and momentum today. We'll go over that. We do some examples. Next class, we'll talk about principle of angular impulse and moment. So again, we integrate Newton's second law with respect to time. So let me just write it here. First one, we'll add to this in next class. Today, we'll talk about principle of linear impulse and moment. All right, so starting with Newton's second law, as always, that's what we have, right? So summation of forces, we know, should be equal to ma, right? Dynamics, things are moving. You can rewrite that as summation of forces is equal to m, this acceleration. So the acceleration is nothing but the derivative of velocity with respect to time. And then move things around. Right? It's pretty straightforward. Summation of forces dt, time changing from some time to another time, some time period, t1 to t2 is supposed to be t1, is equal to m v2 minus m v1. It skipped one step. The other side becomes integral dv from v1 to v2. So this is integral dv from v1 to v2 m, right? Just calculate that integral. M is constant in our case. We're not going to deal with systems that their mass is changing. We're not dealing with any fluid flow. So that's not the scope in this course. You'll deal with that in fluid mechanics. It's not something that fits into the scope of this course, but you'll deal with it in fluid mechanics. I'll see. Actually, you're going to use momentum methods to derive some relationships and equations there. Here, we just assume that mass is constant over time. And that integral dv from v1 to v2 becomes mv2 minus mv1. Now, this part, right, the left side is a linear impulse. The right side, well, mv is linear momentum. So this is change in linear momentum, right? Change in linear momentum. Given that, let me write it here. Momentum, linear momentum, depends on who you talk to. They represent it with different parameters. So I'm just going to write it as linear momentum is equal to mv. This is the definition of a linear momentum. So that mv2 minus mv1 is change in linear momentum. So this is principle of linear. This is basically the principle of linear impulse and momentum. What does that tell us? It tells us the impulse, the linear impulse applied to an object, right, during an time interval of time, like from t1 to t2, is equal to the change in the object's linear momentum. So that's if you want to write it in words, this equation, that becomes principle of linear impulse and momentum. Let me write it this way. So the principle says the impulse applied to an object during an interval of time, right, is equal. Sorry, technical problem here. There you go. Is equal to the change in the object's linear moment. That's the principle of linear impulse and moment. Now, you can define impulse force. Basically, this force as a function of time, you can think about that as some kind of, let's look at it, or let's think about it as some kind of graph like this. Let's say you have a force as a function of time. So T1 to T2, whenever the force is applied, let's say the force is applied from some goes up and then goes down, some from, it's applied from T1 to T2. Right? Let's say this is your force as a function of time. That's basically impulse force, a force that acts over an object in a small interval of time, but exerts a significant linear impulse. It's called an impulse force. That's basically when we use this principle of linear impulse and momentum. So you have a large amount of force applied to an object in a relatively short period of time. Now, you can think about that principle in terms of an average value, right? You can, like, if this is your force is applied in some time interval to an object, you can think about it as an average. Whatever is the value of the force in this time interval divided by the time interval, right? So you can find the average force. If this is your force as a function of time, let me do it this way. So the area under this is integral from T1 to T2 f dt, right? This is the basically the integral, the left side of that equation, the linear impulse. Now you can think about this in so many cases, since it's happening in a short period of time, in a very small time interval. Let's say we are applying a huge amount of force, let's say in an accident, right? A car hits a wall. In a fraction of a second, a large amount of force is applied to the car. That's an example I can think of. When you are I guess that's less common, less straightforward example. But if you think about manufacturing processes, when we are doing punching or pressing some plate, some piece of metal, right? That's also where you see a large amount of force applied to an object in a short period of time. Right? The press comes down, it hits the plate. It makes a hole, or it's supposed to bend the plate. You are going to have a large amount of force applied to an object in a very short period of time. That's impulse force. Now, you can, in so many calculations, we can estimate this one as an average, right? Instead of, you might not have the exact curve force as a function of time to calculate this integral, but you might have the force, average force, and you might have the time period. Let's say on average in this press, in this machine there, we have a press that is applying 10,000 kilonewton in 1 second. So that would be your average force in a short period of time applied to the system. Instead of having that exact curve and finding that integral, we can actually do that and make that kind of, I don't want to say simplification, but approximation. All right, so let's say for average, in average, I can write like this. Average, basically it makes your life easier and you can actually solve problems with some given information. The average force, I show that with summation of force average, is this integral from T1 to T2 sum of the force, or the, if I can fix that, from T1 to T2 forces dt over the time period, T2 minus T1. If I move things around, take T2 minus T1 to the other side, average force is equal to integral from T1 to T2 summation of forces dt. Then that I know from principle of linear impulse and momentum is mv2 minus mv1. So that happens. What comes out of this is that you can think about this as delta t. That'll give you a relatively straightforward relationship. So summation of forces average delta t is equal to m delta v. So this one is trying to tell us that if you know the average force and the time that force is applied to the system, all that is equal to mass multiplied by the change in velocity in the system. that's another equation that I used to use red, so probably have to follow the same standard. This is also a very important expression. I wrote a lot around it, so I don't know how to box it, but I'll do with the danger of making things a little messy, but that's important. All right, so either you know force as a function of time exactly at any given moment in the form of some curve, you know, the force is known as a function of time. So we can directly use principle of linear impulse and momentum and find a change in linear momentum, or find the relationship between change in linear momentum and linear impulse. Or you just have the average force and the time that the force is applied to the system, then that would be another approach that you can just approximate the change in velocity in the system. So one thing you have to pay attention, aside from the fact that principle of linear impulse and momentum is about relationship between force and time, versus when we were talking about energy methods, right? We were talking about relationship between force and displacement. Another thing that is a big difference between momentum methods and energy methods is that in energy methods, when we were talking about principle of work and energy, we only cared about magnitude. I remember it was 1/2 mv squared. We didn't care about the direction of velocity, and we could not deal with the directionality of velocity. The equation was a scalar equation. It could only give us a change in the magnitude of velocity. Now, in momentum methods, though, again, the direction comes into play, because the equation is a vector equation. Right? You have velocity as vectors, you have force as vector. There is no squared. So now you can determine the change both in the magnitude of velocity and its direction. So that's another big difference between momentum methods and energy methods. I'm going to repeat. In energy methods, we only cared about the magnitude of velocity. We could not study the change in direction of the velocity. Remember, velocity is a vector, so both its magnitude and its direction can change. In momentum methods, though, we do care about directions. So we are going to have to pay attention to positive, negative. If you're in two-dimensional space, ij, right? In x direction and y direction. Direction matters, bottom line. We study both the direction, change in direction, and magnitude together. So keep that in mind, all right? Take a note somewhere around, somewhere, keep that somewhere, mentioning that that's another big difference between momentum methods and energy methods. All right, let's take a look at 2 or 3 examples and see how does this work. All right, we at this point we're familiar with forces. We know how to draw free body diagram and study forces. We're familiar with velocities. So all that matters is just to apply this equation to the system we are studying and make sure that the directions are right. We identify parameters correctly. All right. So let's look at the first example. The first example is actually relatively straightforward. So we have, let's write this way, in a test of an energy absorbing bumper, right? It's a car manufacturing environment. They're testing different bumpers, see what bumper could be the best bumper for a car, make the car the most safe as possible. A 1,400 kilogram car, probably a sport car, is driven into a barrier at 4 meters per second the duration of the impact is 0.4 seconds. It's pretty fast. Imagine you have some slow motion camera. Well, they do have a slow motion cameras with capability of recording with very high frame per second. They record the accident, the time of impact that from the moment the car hits the barrier till the moment it bounces back is about 0.4 seconds. When the car rebounds from barrier, the magnitude of its velocity is 1 meter per second. So part A is asking us to find the magnitude of what is the magnitude of the change in horizontal force exerted on the car during the impact. Right, so let's just solve the first part, then I'll talk about the second. So going back to simplified version of the equation, this one, right, when we're dealing with average force, or we're given the, or we're looking for change in force, want to know what is the average force. We are not given the exact way the force is changed as a function of time. We just use this relationship, right, for approximating. So let me just look at the equation and write it here. Summation of forces, basically average forces delta T is equal to M delta V. All right. Now, what do we know? So we are looking for change in horizontal force. So obviously we're looking for the force. Summation of force average is equal to. Let's expand the other side, mv2 minus mv1 over delta T. Now we know the mass of the car. We know the velocities, 4 meters per second when it's, let me draw it here. So here is the situation. We have, draw best I can for. All right, not bad. We have a barrier here. This car is going towards it with 4 meters per second. It hits the barrier. The impact takes 0.4 seconds. It bounces back with 1 meter per second. So pretty straightforward. We have velocity before impact, velocity after, right? mv2 minus mv1. We know the mass, we know time difference. We can find the amount of force, average force applied to this car during this impact. Now, one thing you have to pay attention, that's the point I was emphasizing, that now that we're dealing with momentum methods, direction matters. So you have to take one direction as positive, up to you. As long as you have some sense of positive, negative, some sense of coordinate system, you are good. All right. Let's take this as positive. or we can think about this as x and y. That means when the car is about to hit the barrier, the velocity is 4 meters per second and is positive. And when it bounces back, it's negative. Now, if you take it the other way around, right? If you say, well, I don't want that, I want to take this as positive. Then it means that 4 meters per second is negative before impact. And once it hits the barrier, it bounces back with 1 meter per second. So you're going to have your V1, if that is going to be a positive direction. Let's see if I can. It's going to be positive. Your V1 would be minus 4 meters per second, and your V2 would be 1 meter per second. That's one thing I wanted to emphasize in this problem. In momentum methods, direction matters, as opposed to what we had in energy methods. So let's put this as minus 4, put this as 1 time is 0.4 seconds. You actually can get your average force. That will give you 1700 newtons. 1700 newtons to the right, right? It turned out to be positive, and that's the direction you took as positive. If you took the positive in the opposite direction, you would have given this, I would have found this as negative, which meant still that the force is applied to the right. So as long as you have a sense of direction and some coordinate system somewhere, x, y, z, if you're in three-dimensional space, it's pretty straightforward, but that's something you have to pay attention to. Right? In just one direction, I would say one-dimensional space is relatively straightforward, it's positive and negative. Once you get into two-dimensional space, you have to pay attention to components along x and y axes. We'll look at those. All right, so again, here is the story. Right, just want to make sure that you all follow what's happening. Talking about energy methods, momentum methods. There is some force applied to the system in a span of time, in a time interval. As long as we know about the velocity of the system before and after the force is applied, we can apply this relationship, right? Or if that's something we are interested in, right? We can form a relationship between the force applied to the system in a time interval, in a span of time, and the change in the velocity of the system, change in linear momentum, as we call it. That's the story. Previously, we were looking at the relation between force and displacement. Now you're looking at the relationship between force and time. Both are coming from Newton's second law. We just integrated Newton's second law for energy method with respect to R, or position. We integrate the momentum method for with respect to time. Newton's second law with respect to time for momentum methods. That is correct. It should be, sorry guys, yeah, you're right. I put the wrong value from my note. 17,500 Newton. Thank you. Awesome. So not everyone is taking a nap. I am glad. All right, part B. What is the part B says what is the acceleration of the car during the impact? Oh, that's from what we know from before. That's from kinematics. So what is the acceleration of the car during the impact? Well, what was acceleration? Acceleration was definition. Acceleration was change of velocity over time. Well, we know change in velocity, right? It's 1 minus 4 divided by time 0.4. It's pretty much it. It becomes 5 over 4 over 10, 50. This should be 0.4. Right? How much does that become? Okay, now that you're calculating, tell me what that is. 50 over 4, whatever the value is. 15, all right, 15 meter per second squared. Yeah, that's not 50. Why do you guys get 12? Okay, yeah, that makes more sense. 12.5 meter per second squared. That becomes the acceleration. All right. All right. Let's look at an example that we actually know the force as a function of time. Also, a little more advanced stuff. And this is pretty straightforward. Just wanted to demonstrate the cohesion and paying how you have to pay attention to directions. All right, next example. Any question on previous example, guys, before we move on? Aside from the fact that I didn't know the final numbers. All right, a question there. Now let's look at this case. Let me draw the force as a function of time here given for this problem first, and then I write the problem statement, tell you what the story is. This is force. This is time as second. This is force unit Newton. We have force as a function of time in this form. Here is some information about this. This is, I can do that. This is 50 newtons. This is 4 seconds. This is 8 seconds. And this 12 seconds, probably not in the scale. And yeah, that's it. So let's see the problem statement. So it says the 10 kilogram box starts from rest and is subject to the horizontal force described, let's say in the graph. In the graph. Right, so we have a box sitting there on the ground. The force F as a function of time, as showed in the graph, is applied to. Now, it says the coefficient of friction between the box and the floor, let's say, is, well, to make our life easier, they told us that coefficient of static friction for static coefficient of friction for static and kinetic are equal, which means this should be mu k, and that's 0.2. So coefficient for static friction and kinetic friction are the same. Determine how fast the box is moving at t equals 12 seconds. All right. So once we are done applying this force, the force starts from 0 right there, and keeps applying, it goes up, gets to 50 newtons. It stays constant from 4 to 8 seconds, and then it goes down to 0, becomes 0 at 12 seconds. Now, where is the trick? Right? Remember, the equation was this one. Right? We were looking at this equation. F dt, now I'm going to write it in integral form because we have the force as a function of time, is equal to mv2 minus mv1. And from t1 to t2. So summation of forces, we have to kind of have an eye on free-body diagram. If this is my box sitting on the ground, let's see what forces do I have there. I have a bunch of forces there I have to take into account. Well, the first one is the F, as stated by the problem, applied to the mass, to this box. I have my normal force and weight, and I do have my friction. So that's mg, that's n, and since the motion is in this way, this is f. Let's write it as mu n. Now, I have to find the summation of forces. So summation of forces, well, I have my friction, I have my the force applied, external force, I have the weight, and the normal force. Now, let's see what is happening here physically and just take a moment and analyze the situation. So the box is sitting on the ground. We start applying the force. Force is 0, and it slowly increases up until 50 newtons. So one thing immediately we can figure out is that, well, since the motion starts from rest, velocity is 0. V1 is 0. That we can agree on. There's no argument there, hopefully. Now, the problem is, if I write this, the left side, right, that integral equation, from 0 to 14 seconds, like that would be the first thought that comes to mind, that just calculate the summation of forces, and from T1 to T2, and then, it's pretty straightforward. You can find the velocity, V2. Now, that's what I'm talking about. I'm going to write it here. So V2 becomes basically the integral summation of forces dt from T1 to T2 m. Right? Now, the trick here is, of course, there's a trick. When does the motion start? We have a friction right there, and the friction is stopping the box from moving at the beginning. You have to have enough force to overcome that friction and start the motion. Now, the question becomes, what is T1? Like T2 is the end of the motion, 12 seconds. What is T1? When does this motion start? There is a period of time that you're pushing the box, right? But the box is not moving because your force is not strong enough to move the box. So you have to find that sweet spot when the box starts moving. And that would be the time that your force is equal to the friction force. So you have to calculate the friction force, right? and find out how much is that. Now, when your force reaches that force, the friction force, and since mu s and mu k are the same, that's the moment that the box starts moving, and then it keeps moving afterwards. So our goal is to find the friction force and figure out how much force we need to apply basically to overcome that. And that's when the motion starts. That would be the time. Knowing that force, we can find the corresponding time, and then that would be the time the motion starts. Remember, this is about the motion. We don't care about the box sitting on the floor. It doesn't matter how much force you apply to it. It is always at rest until you overcome the friction. So with that, I'm going to calculate friction. I didn't put Fk or Fs because mu s and mu k are the same. Mu n. Now n is mg. So mu mg. That becomes 0.2. M is 10 kilograms times 9.81. That becomes 0.2 times 98.1. What I got was 19.6. Since I'm always wrong today, we'll see how does that. So that's friction force. So this motion starts the moment you reach that force. When do you reach that force? Well, that's that's when that force time graph comes to help you, comes into play, at least at this stage. You know force as a function of time. So the moment you reach to this force magnitude or value can be found. If this is 50 newtons, I'll say it's somewhere here, 19.6. So here is the time T1 we're looking for. Before that, nothing is happening. After this is when the motion starts. Now, since you have these two, you have the relationship between force and time, you can actually find where that time is. If you look at these triangles, I'm going to magnify them here. So here is the situation. We have one triangle here, and we have another triangle there. Now this is 50, and this is 4. This is 19.6, and this is what I'm looking for. Two similar triangles. So 50, you can write it this way, 50 over 4 is equal to, let me write it maybe where this is. I don't know, might make more sense. 50 over 4 is equal to 19.6 over T1. So you can find your T1. Your T1 becomes, well, let's just keep it as T1. Let me write it. Did I write it in a good way? I think it is. T1 becomes 4 times 19.6 over 50. I got, yeah, today is not a good day for my calculation. I got 1.568 seconds. Hopefully that's the number, because I did the rest of my calculation based on that. Once we know the time that the motion starts, then we can write it, we can put that as the beginning, right? So this equation right there, let me bring it here. Now V2 becomes from T1, which is 1.568, to T2, which is 12 seconds, the force, summation of forces dt over m. Now, once you overcome friction, whatever is left is just the force applied to your mass. Right? Then this integral is nothing but the area under this curve, but minus the beginning, right? The beginning basically was not wasted, but it was used to overcome friction. So this is the area you're trying to find. This is integral from 1.568 to 12f dt. You find that the area, well, the way you are most comfortable with, say 50 times 4, the middle part, then you have a triangle on the right side, and then you have the other part. I'll do it this way. I don't know, it depends on how you are more comfortable with. So let me write it this. I'll say 50 times 8 minus 4 for the middle part. Then we have the right side plus 50 times 4 divided by 2 plus, just cutting it into different sections. The left side, 50 plus 19.6 divided by 2 times the height. So I'll write it this way, 50 plus 19.6 divided by 2 times fraction times the height. And height would be, you can do better, 4 minus 19.6. Divide the whole thing by the mass, which is 10 kilograms. Basically, I just calculate the area under the curve. You do it the way you feel more comfortable. There was a rectangle there, triangle on the right side. You can go for the left side as a big triangle, 50 times 4 divided by 2 minus the small triangle. That's another way of doing it. 19.6 times T1 divided by 2 to find that area right there. This is, let's see if I can identify that. This is this area. This one is this area. And this is this area, basically. You do the math, you'll get V2 as 18 meter per second. Hopefully I did it right, everything there. So, as easy as it looks, can be very tricky, right? You have to look at the physics of the problem. When did the motion start? We had to go over multiple loops to figure out when does this motion start. You have to remember that the motion starts the moment you can overcome. 4 minus, yes, it should be. I don't know why they put 19.6 there. Today is not the day, apparently. T1 was 1.568. Hopefully I did not make a mistake with calculation. This is very dubious. Double check this number. It's a very straightforward 18, so it might be something wrong. The fact that it's so round. But the procedure is hopefully makes sense. Question on this one, guys. Question on this one. got 38. Yeah, it's very off from 11. Okay, so good. I'll go with your number because definitely mine is 38. All right, it's good. 3 out of 24. I accept that. All right. Question on this one. All right, so let's do one more example before we jump into quiz. I just want to show what happens if you're in two-dimensional, or it's not just in one-dimensional, if you have XY components, right? And the story is we have a baseball. Let's put it here. We're going to see this baseball over and over when it comes to impact and analyzing, because that's an area that makes a lot more sense, I guess, thinking about impact when we hit a baseball with a bat. We have the ball. Let me draw this and then I'll explain. I put the coordinates there. It's going this way with its 800 grams. Velocity is 20 meters per second. This is point A, and then it comes here, and then it goes in this direction after the impact. I can probably do a little better. And the velocity for that is 40 meters per second. And this angle right here, 40 degrees. Here's the story. We have an 800-gram baseball, right? Someone throws this like horizontally towards a batter there, right? The ball is hit. Its velocity is 20 meters per second. We have some fancy camera can measure the velocity of the ball. After it's struck by the bat, right, at point A, this ball is going to have a velocity of 40 meters per second in this direction. Now, what we're trying to find is to find the magnitude of the average force. So now we know how fast it's coming, how fast it's going after the impact, right? And we are estimating that impact duration is 0.2 seconds, 0.02 seconds, so a very short amount of time. We want to know how much force the batter, the person who hit this ball, applied to this ball. All right, so here's the story. Let me write it. The 800-gram baseball is thrown horizontally toward toward a batter at 20 meters per second after being struck by the bat, let's say at point A. The velocity of the ball is 40 meters per second in the direction shown. In the direction shown. Right. Find the average force applied to the ball if the duration of contact is 0.02 seconds. I use the average equation, summation of forces, or you can just write it this way. Summation of forces average delta T is equal to M delta V. We are looking for the force, so summation of forces average is equal to M. This constant, so I'll keep it outside, over delta T is 0.02 seconds. Now we know M is also given 800 grams. Let me follow the same procedure. Delta T here, delta T is given as 0.02. Velocities, right? That's the tricky part. We have to take into account the direction. That's basically the point of this problem. I want you to see that direction matters when it comes to momentum as opposed to energy. Now the velocity before impact, V1, it's 20 meters per second to the left, so minus 20I. Write it in vector form. It's probably the easiest way of doing it. Velocity 2 after impact, we have 40 meters per second, makes a 40 degrees angle with the horizontal line on x-axis, so that becomes 40 cosine 40 degrees I plus 40 sine 40 degrees J. And that's what you do. Just that's all added to the story, because we have to take the direction into account. Right? I wrote it in vector form because it's two-dimensional. In one-dimensional, as long as you know positive and negative, you're good to go. But once you get into two-dimensional story, you have to actually represent them in vector form to make sure that things don't get confusing. You can replace these values. Right? You get 0.8 times 40 cosine 40 degrees I plus 40 sine 40 degrees J plus 20J divided by 0.02. So that gives you the average force. It's division, so divide each component, sum up these two. This is J and this is J. Divide by 0.02. Here is what you get. You get 222 point. Hopefully, again, this is also correct. Today I'm just getting wrong numbers. 0.5 I plus 1028.5 J. And you can find the magnitude. Just want to wrap this up of the force. Right? This would be squared plus this squared gives you 2451.66 newtons. All right, let me just jump into a quiz. I know I wrapped it up fast, but all right, folks, just let's get